I know.
Okay.
I'm still worried that I Isorundo can't see.
Yes. Thank you. Okay, let's continue discuss this example before we go to the general perturbation theory. Remember, we consider the charge is a mass F. In this, the potential is a one-dimensional harmonic oscillator. This subject and weak electric field. So the electric field epsilon is very big compared with the H naught. So we can consider this term as a perturbation, right? Then the Hamiltonian is the unperturbate plus perturbate. Now, first, this solution actually can get the exact solution because we may manipulate but introduce y hat as xi plus some constant. Then we can see the Hamiltonian return in term of y. Actually, it is a perturbation term plus constant. So the solution we already solved in the chapter 4, energy and states. Now we are going to apply the perturbation theory to obtain initially from the unperturbed term and this one to see how can we get this solution compared with the exact solution, right? So how to do that? Okay, we first go to the first, just remind you, same thing like this. So we have E, I'm going to say perturbate 1. If I use P means I already include lambda. Remember that I used. So that's just the matrix element of HP between the states, right? So that is n states. That is n zeroth order and HP. Okay. So now we are going to apply here, right? So now let's see this one. So we substitute this. This is HP. That is constant at the outside. And here, set n x. Remember this one? Okay. If I use this, we introduce number, right? Number operator, it's something like this. Right? How much? This will be 0, remember? Okay, let's try to remind. So remember, let's look at this general. This matrix element of x between the two states. Now I'm going to use m because later you will see this 0, so I go to the second order correction. H bar m a plus a. Remember this? Yeah, that is x, right? So we know this is lowering this raising, and what we know is by lower or raising by 1 unit, right? 1 number. So then the inside here, this one, the next test. Okay. This one is square root n minus 1, right? The lowering. And this is the raising, that is n square root n plus 1, n plus 1. So by the normalization of orthogonal of this, then the result, only there are 2 non-zero results. Which one? N, this is n is equal to n minus 1, right? And another term, n should be n plus 1. So then you come to here. Then this, when x apply this one, either n minus 1 or n plus 1, so that is 0, right? Okay, so that means up to the first order, there is no any correction, so we have to go to second order. I'm going to use P again to the lambda square. So second order, if you remember, we just, if the formula is the last case, that is m not equal to n, and E and this is a square of this product of HP between the two states. Square, right? That is the general formula. So now we are going to apply to this case. Okay. Let me still keep here. Denominator still keep here. Inside here, HP is Q epsilon, so I take the Q epsilon outside, right? Q square epsilon square outside. The inside is this, right? Inside is this one. So that is here, right? So that is summation. Okay. Here, that's being careful. Okay, let me do this. Delta n minus 1 plus n plus 1 delta n plus 1. So now you can see if m equal to n minus 1, this term is non-zero. If m equal to n plus 1, this term is non-zero. So we have only two terms non-zero, right? So that term is, the first term is m equal to m minus 1, right? Oh, sorry, this is n. Yeah. And then this one is this term, right? So that is an n squared is n. And here I have those, right? So h bar omega q squared h squared. And another term is m equal to n plus 1. And here n plus 1 is n plus 1. Then we have h bar q n omega q squared h squared. Now here, this is an e. And okay. This e not without this term, right? Is this term, right? So then you can see here, this one is h bar omega, and then you see this one is negative h bar omega. The difference between the lowest, the nth level and n minus 1 level, that is positive because n minus, yes, n minus n minus, right? So that is difference just this h bar omega. You see, but they were n change increase 1 and decrease 1, that is only 1 h bar omega. Here, this is higher than this one, so it's positive. This is lower than this one, is negative, right? Then you can see here we have a negative sign on here, so you have minus n minus 1. The minus n cancel, only the minus 1, that term. So finally, that is this term, which is nothing but the constant term here. So you will see here, so then we can find the energy correction, in this case, is to be the zeroth order plus first order plus second order. But first order correction is 0, so only the second order, right? And then that is n plus half of h bar omega. And then this one is minus q squared and epsilon squared to m omega. And you can see exact equal to this. So that shows how powerful this perturbation theory, and up to this case, up to second order is enough. Okay, so this is just an example for the non-degenerate. Now we go to the degenerate case. If we have a degeneracy, how to make this, apply this perturbation theory. Generally, perturbation theory. Okay. So the journey, let's first look at this H naught. What that means the journey is H naught, the eigenvalue problem of H naught and perturbation term, we have solved the eigenvalue and the eigenspace, right? So here eigenvalue is this one that correspond to a series. Now I'm going to use index of in alpha, so alpha from 1. So how much degeneracy? Right? Since for given energy, we will have how many states? You have F states. That we call the degeneracy, right? So that is the, I'm pretty big, if we already know those, that is the exact solution if we know. Then now, what happened? So if we have this perturbation term, and here, so what happened? Here, okay, so that degeneracy is due to, usually it's due to high symmetry, right? Because high symmetry, so we know the higher, in particular like hydrogen atom, right? We have a spherical, the potential spherical symmetry. So that is highest, then we know the energy only depends on quantum number n, but the states has a quantum number n, L, n. So we have a 2n, actually it's n squared, right? I mean this, the degeneracy. So now, this one, here, this one is a high symmetry, usually. So therefore, we have degeneracy. So this one is low symmetry. For example, here we add this electric field. It's only along a certain direction, so that is the symmetry only this along this z-axis, right? Now it's whole spherical. So what happens? If the symmetry of the perturbation low, so the total Hamiltonian is lower, right? The total Hamiltonian, the symmetry is lower due to the perturbation is reduced by the perturbation term. So that is the difference when we discuss non-perturbation, non-degenerate. We just consider perturbation contribute to this zeroth order. But now, for the degenerate case, the first issue is try to left the degeneracy, right? So that is the first, and then but when we left, then we can after lefting the degeneracy, the more correction is from this. We can apply the non-degenerate. So here, okay. So key in this case is, yeah. Therefore, the energy here is equal to, right, plus sum of a correction. I'm going to use this one. This one will left the degeneracy. And maybe totally, or partially. So depend. So maybe we add this perturbation term is totally left all the degeneracy and the energy became non-degenerate, or part of them left it, but they still have some of other degenerate. So that is the case. Now, with this case, so we are going to see how to correct or left this degeneracy, So now, let's look this what happened. Okay, so here, this one, the subs, for given n, we have F states, right? Eigenstates. This one form this complete sides, which is forming the subspace. Right. So, for example, we consider hydrogen atom, right? the hydrogen atom for given n, even for given L, we still have 2L plus 1, the M values. So those M, different given L and those different M states, they form the subspace. So in this subspace, any function can be expanded in terms of this because it's complete, right? That means expand all this, all this for given n and L, all the others are the linear combination of those different M. So let's consider that is we are going to solve, right? Actually here, now I'm going to, here this one I'm going to use beta, since let me write down it here, and then I'm going to expand beta. So here we have F, these states, and those states correspond to the degenerate energy E. But for those F states, we can manipulate by linear combination of those together such that we can build up new states, right? So those new states, now I'm going to beta still 1 to F. How many? We can, depend on the coefficient here, we can construct also another F orthogonal, right? So these are something like, remember if we have x, y, z coordinates, but we can also use like x prime, y prime, z prime by rotation. And that is another set. Also, they are orthogonal, and then we can find the relation between these two. So x prime, y prime, z prime is function of x, y, z, right? With the sum, something like that. So now what we do is, okay, we are going to solve this one, which the Hamiltonian has a perturbation term. This new wave function is nothing but a linear combination of those original and perturbation term. So they are all in the same space, subspace. That is the idea. So here, okay, now just let's use this one. Okay, here, just the orthogonal of this. Okay. All right. So if I use 0 means I'm perturbate, right? And beta and alpha, beta alpha, right? This is orthogonal. That is, then we can, for all this orthogonal, definitely means they are independent, right? Linear independent, so any linear combination of linear independent this function can form the other one. And we are going to build the other f, which is from here by different coefficient. So that is the idea of this. So once we have this, now let's think about this Hamiltonian. So this eigenvalue problem, right? So now this is now I'm going to here. Let me use n, and later you will see this index will change. Have another index since we left the degeneracy here. Right? So I keep here, but then later you will see that. Right? This is the same as this one. But now I'm going to just this one is introduced by the linear combination of known eigenstates. So now this is we're going to solve, right? And how to do that? That means we are going to, this one is and perturbation energy plus correct part. So we are going to look at this one, right? This is our goal. So how to do that? This is a can. Then if we use the bra to multiply, then this became a number. Then the remaining part is like matrix. So now let's multiply. Right. In beta. Since this we know, right? Multiply this, then we have this left-hand side and sum. Okay. Okay, that's first. And sum. Okay. And sum all the beta. If I use beta, okay. call this. At first the subject of it, so here that is HP linear alpha, right? That is summation for alpha from 1 to F, A and alpha beta, psi and beta, this order plus here I was going to answer this. Okay, now I'm going to multiply. Multiply, draw, and that's it. So the left hand side is, let me move this summation in front. And here that is m beta. Oh, sorry, it's H naught. Okay. H naught plus HP here. Keep this constant here. Keep constant here. And beta. And here is 0. Equal to summation of 1 to F. So now here, we know H naught apply this give us E and naught, right? So that is the here. That is this one, right? Not to make details. So here, the summation from 1 to A and alpha beta. Inside, this is the E n naught and delta alpha beta, right? Since this one and this one, they are orthogonal here. And the second term is the matrix element of the HP between this and perturbation term states. Okay, that is the left hand side, and the right hand side from 1 to F, E n, A n, alpha beta, delta alpha beta. This is the orthogonal. Now let me move all this term to the left hand side, so you will see this is a group of homogeneous linear equation. From 1 to F. Okay, so I'm going to keep this one at first. Yes, I just immediately write down here. H P beta alpha, right? Is this one. H beta alpha, which is element. And the minus, now I'm going to E n minus E n naught delta alpha beta A n alpha beta equal to 0. Right? See here, I take this term to the left hand side so that I have a negative sign, and here positive with the negative become positive this term. And we multiply this delta function, then now you can see this equation is for all the alpha from 1 to F to solve this one. This is unknown coefficient. So this is a linear equation, right? And to for the solution, right? So now the solution for now 0 A and alpha. A linear equation, we know that that means the determinant of this should be equal to 0, and this is what? This is the determinant of HP. So, okay, notation 1, let me see, yeah. HP beta alpha 1 minus En. Okay, now I'm going to introduce En1. So now here the difference, let me first write down and then let me expand. 1, 1, 2, P1F, and P2, 1, P2, 2 minus En, because it's only diagonal, right? And P2, 3, P2F. So finally it's Pf, F1, and Q, F minus En1. Here, En1 is the energy difference of this, we are going to obtain the total, subtract and perturbation term. So now, the remaining job is we are going to solve this, right? So by solving this, we have the result or root for a series of this, right? By solving this. This is an F by F square matrix, right? So by solving this, we will have, in general, we have the F value. Now I'm going to get the index. Let me see, I use beta, okay, let me use beta. So now the beta equal to 1, 2, to F. Usually we will have beta roots, but maybe some of them are the same. If some of them are the same, then that means partially lefted. If all the values are not the same, so that means if a totally different, so that means total, totally left. If partially different, that means partially left. Partially. So this is the way when we have a diageometry, we first step actually is just try to reduce this diageometry or left diageometry. That is a correction. Then that is for energy, right? So then for the states, we need a coefficient here, right? So how to obtain A and alpha beta? What we could, because from this linear equation here, that is what we have to do is solve the eigenvalue problem, right? By of like this here, right? So we have a matrix H P11, H P1F, HPF1, HPFF, with this the AN1 beta, AN2 beta, F beta equal to the energy, which is we solve here, right? En1, but En1 now N is also has another index or quantum number beta, since after solve we will have F values. And this chapter 2, we have solved this kind of matrix representation, the eigenvalue problem, right? So by those we can solve this.
Dr. Yu,
Yes.
when back with the energy, where you say if it's totally different versus partially different,
Yeah.
do you mean like each term of your diagonal, if each term of your diagonal is totally different?
No. This is you mean this diagonal we are going to solve, right?
Right,
After solve that, we are going to find all the value for this one.
okay,
So this one, if all the value in the depend on, for given n depend on beta, if all the beta value are totally different,
okay,
that means all the degeneracy left. If the value, some of them still have the same value, that means still have a partially degenerate.
okay, so
Yeah,
for
that is-
each beta,
For each beta, yes,
okay,
this has beta. So we are going to do one example, you will see we will have this kind of examples, then you can. So now, this is a story, right? We can find, so finally let me summarize. So energy here, now I'm going to introduce another index here because now the correction energy is has depend on another, for given n we have a beta, right? So now the total energy also, n zeros does not have a beta, right? Because it's a degeneracy, and then plus en beta 1. Okay, so beta 1, 2, you have total F. So that you see, the total energy now is for giving the unperturbed n, but we have F values. That is change, or left is the degeneracy. And state, so n beta, right? So this states the linear combination of beta, psi, n alpha. And here, we obtain from here. So this coefficient, we may know the coefficient we can find each correspond to the beta. We will have our corresponding energy for one E and beta we have states. Now this one is by solving this. So what's the step? For degenerate, first you find this matrix element of a perturbation term between these unperturbed states, and then build up this matrix and calculate the determinant to be 0, so we can find the roots. That is for this energy correction. And after that, we are going to solve the eigenvalue problem to obtain all the coefficients, and then we can have these final correct states. So that is a different strategy in this degenerate. Now let's do one example, see how can we apply. This is called the Stark effect. What is Stark effect? It is the hydrogen atom. So we have a hydrogen atom placed in a weak electric field. Something the previous example for the one-dimension harmonic oscillator. Here, this hydrogen. Right. So then, when we place, because we know the hydrogen atom is Hamiltonian H naught is a high symmetry, spherical symmetry. Then, let's say along z-axis. Okay. So that means this one perturbation is only along the axis, so that totally reduces the symmetry, right? So now, ask it to find. Okay. Find the energy level of n equal to 2. See here, depend on n. So let's just select n equal to 2. The others do the same thing. So now, let's do that. We know this Stark effect means that when the hydrogen atom placed into the field, you will see like Zeeman effect. You see energy level split into several sub-levels. That is increased. So okay, first H naught. Just remind you know the H naught, right? So H naught, the solution is this degenerate, is highly degenerate. So here, En is minus E naught or n squared. So E naught is 13 or some numbers, okay, I just gave you numbers, but you know where number come from, right? N from 1, 2, so that is degenerate, okay, degeneracy, psi n L m is R and L, radial part and angle part L m, right? Ignore spin. So how many for you need the degeneracy? It's n squared, right? For given n, we have L from 0 to n minus 1, and for given L, we have 2L plus 1. In chapter 6, we already know. So this is really highly degenerate. Now means for given n, we will have those states. Okay, now let's read the perturbation term. Perturbation term is minus the electron dipole moment, inner product, and the field, right? So electron dipole moment for electron is negative and plus, right? And z direction. So that is perturbation term. Okay, so now what we are going to do is for n equal to 2. Let's consider for n equal to 2. Okay, so how many, let's just look, how many states? So we have 2 LM, we have 2, 0, 0, L equal to 0, right? And 2, 1, 0, 2, 1, 1, and 2, 1, minus 1. 4 states. So for n equal to, and here also, 2 squared is 4, right? So that has a 4 by 4 or a 4 degeneracy. Now, yeah, I just read. So now the next, the first step is we are going to solve this. Now I'm going to use 1, right? I'm going to solve this, right? So here, first you need to calculate this one. H P alpha beta in this case is H P. So 2, right? L prime, M prime, and here E epsilon Z 2 L M. Right? That is this in the product, right?
Do we need to consider the spin?
Yeah, I just ignore spin here. In this case, ignore spin.
Okay.
Yeah. If we consider spin later, we are going to discuss this spin outflow effect. Then in that case, so that's case. In this case, let's just make it simple. So here, this one, the key is for each, for this L and L prime and prime and L m, then we will have how many? 4 by 4, 16, right? 16 measured element. L prime and L from 0 to 1, and N prime and N is 0 plus minus 1, right? All this not way. So totally we have 16. Now, this is a time consuming. We need to do the calculation. And how to do the calculation, I will give you this formula and some of symmetry analysis, and I will not spend too much time. So now, let's look here. Okay, just consider this one. So, because Z is R cosine theta, right? So this one, 2L prime M prime Z, 2LM is 2L prime M prime R cosine theta, 2LM. And here, the R part is 2L prime R to L, right? Only radial part. And then this is L prime M prime cosine theta. This is only radial part, right? So your integral has this one and this one. Okay. And now this one, we are going to use the, remember we have several recursion equation. This one, so cosine theta, if you look at the table, chapter 6, you will know this cosine theta is correspond to 4, 9, 3, y, this one, remember? So that is actually it's nothing but the spherical harmonic correspond to L1 and equal to 0 term. So now, so this one is became like this. So now let's keep this as this one. L1 M1 cosine theta Lm is, let me just give you, is integral for the solid angle by L1 M1. It is bra, right? So theta phi, and then the cosine here. Okay, yes. Cosine here is this constant 3 y 0 theta phi, and then y L m, right? Then you can see here, okay.
Is it y10 because L is 1 and M is 0?
You mean this one?
Yeah, the y10.
No, here, this one is 10. It's cosine, I replace. So this one is cosine theta.
Right.
But these two are arbitrary. It's between L and either 0, 1, and M prime is 0 plus minus. So this one is the result. I'm going to give you the formula is, it's refer the equation in chapter 7, 244. I think we didn't go to that because after we discussed this D matrix, and I just discussed one particular case. So now let me give this one. We just have this. So if any, this is a 3 harmonic function, right? So that is a spherical function. So y L1 M1, y L2 M2, d omega is equal to space here. Is equal to, just go to that equation. L2 L1 plus 1, L2 plus 1 over 4 pi 2L plus 1. And now this is later, this CG coefficient. L1, L2, 0, 0, 0, L0, another L1, M1. Okay, M1, M2, M1, M1. So here, this is a CG coefficient. M1 is 0, M2 0, M0, L1, L2, L. And this one is another coefficient. We have product two coefficient. You can, if we can have a table, right? M1, M2, M prime, L1, L2, L prime. So that is the general formula, and we will not go to the details, and let me just give you the result. The result by analyze some symmetry. So the result is here. 2, 0, 0. Okay. Include here, include this E axis, right? That is the HP. That's an index too much. Okay, let's do this one. 2, 0, 0. HP 200 is 0. And 200 HP 210 is non-zero, which is minus 3 E actually A1. 210 HP 200 is okay. It's also minus 3 E actually A0. Then the others. For others. So the non-zero term is only these two. Okay, then we are going to solve this determinants equal to 0, right? N 1, but in this case 2. Okay, 2 alpha beta, delta alpha beta. This equal to the 0 is not matrix is like this. Minus E2, 1, 0, minus 3, E actually E naught, 0, 0, minus E2, 1, 0, 0, minus 3, E actually E naught, and 0, minus E2, 1, 0, and 0, 0. So finally, you will see not of the element mentioned as 0, only these two terms are not 0. Then the result, just solve this 4x4 matrix. So now let me give the result. This is equal to, I just keep counting, that's equal, that is give us this one, E2, 1 square. E2, 1 square multiply E2, 1 square minus 3E epsilon A0 square equal to 0. So we have how many values? We have 4 values. If we give an index E2 not index 1 is minus 3E epsilon A0. Now the second one, this is like beta, right? 2 is 0. E2, 3, 1 is also 0. So you see these two not lefted, right? And the number 4, 2, 4 is positive 3E. So that means it's partially left degeneration. That means the 4 values, there are 2 different, but another 2 are same. So that means this is not fully, the degeneration is not fully lefted. Okay, I think I did another issue is about R. I didn't give you this, but for R, for this one, here it is. For this one, just go to the equation in chapter, I think 6, right? Chapter 6, I think the equation of the notation summary. You remember that formula? I think the summary chapter 6. Okay, here. 680. Okay. Then the remaining is solve this the coefficient. I want to save time. So for the alpha, for this, okay, 2 alpha beta, just solve this. Matrix P, right? And this A, N, alpha, beta, alpha. So this one, for each one, we have 4 values, right? For each one, we solve this. that is also time consuming, but you know how to do that. We already had a lot of exercises in chapter 2. Okay, so now this shows the example how we use the general case. We need to first solve this one, but of course you need to calculate matrix element. That is, we need to be careful to do that. And then when you solve this, determinant equal to 0, so get the eigenvalues. After getting eigenvalue for each eigenvalue, we are going to solve this coefficient. Now, we are going to discuss very important application for this perturbation theory about the fine structure and anomalous Zeeman effect. So, an application, not the examples, right? So applications. Fine structure. The normal Zeeman effect we already discussed in chapter 6. End of chapter 6, we applied Mach field, right? Remember, that case, the Zeeman effect is interaction between this orbital generated dipole moment with external field. But here, you will see we consider spin. In that time, we didn't consider the right? Yeah. So now, the Zeeman effect, and so now let's first discuss the fine structure. What is the fine structure? Fine structure is includes two effects. Due to these two effects combined together, that is fine structure correct on the those are on hydrogen atom. So when we discussed hydrogen atom in chapter 6, we did not consider, now we are going to do the so-called spin orbital coupling and also relativistic effect correction to this kinetic energy term. So two effects. One is spin orbital coupling. Another is the relativistic correction. Where come from these two terms? So now we are going to analyze. It's because the correction are in the same order. So that's why when we consider these corrections, we also consider this one. Later we will see. They contribute the same order on this level of energy and perturbation term, right? So that is first spin orbital coupling. What is spin orbital coupling? Okay, let's consider. So here we know hydrogen atom, we have a proton here, right? Positive charge and electron move around. That is at the rest of our light frame. So what we see. Or in terms of if we stay on this the frame or rest frame of a proton, so what we see is electron move around. But okay, so this is rest. But if we consider we are stand on the electron, you have question? No. Okay. So if we are here, then what we found the proton move around us, right? So now, okay. Suppose this electron move is counterclockwise, so I'm going to give us the velocity V. Then if we on this electron as this the rest. Rest the frame of electron. What we found is the proton move around And so that direction is clockwise, right? So velocity of proton is just opposite direction of electron. So what happened? Then you can see, because the proton move very quickly, you will see it's like a circuit, current circuit, right? So the two EMM, you know that if we have a current like circle, so we generate a Mach field. This is a top view, so let's use this X, Y, Z. So here, this is an electron here. Then what we found is the proton moves along this in terms of the opposite direction of the electron. So then the current is like this, right? Okay. Let me do this because I want to see that use Z. So now let's do this is not. So this right-hand rule, so we know the Mach field generated by the proton due to this quick circular. So here is a field, right? That is what electron field is inside, but if no any dipole moment, there's no interaction. But here you have a spin, or spin like let's say. The magnetic dipole moment generated by spin. Usually they are opposite direction, right? So what happens? There's an interaction between this. That is spin optocoupled. So for the hygiene item, actually we didn't consider this interaction or contribution to the hygiene item, since this contribution is almost the order of 10 to the minus 4, not very small, so we initially made it. But now we are going to consider, since we have a perturbation theory, so we are able to take into account this effect. So that is spin optical. Now we are going to write down what is the Hamiltonian associated with this one. So here, the field, according to this EMM, we know that is 1 over CV, right? Because the current is generated by this the speed or orbital, right? So electric field should be the direction. Okay, now this positive charge here. So the direction is this interaction, right? Electric from positive charge to negative charge. So that means the velocity, you see, if you cut this across, so that is this velocity, right? So that is field. Okay, and then if I replace the V, the velocity proton by velocity electron, so negative. The E, okay, is the field. Now I'm going to use term of a momentum. Linear momentum, so that is divided by multiplied with ME and divided by ME. So here, negative 1 over MEC, right? And then is the linear momentum. Or if I switch, so we know if a change position is negative sign disappear, right? So that is 1 over MECE cos P. This is a classical. And after this, we are going to convert to this quantum mechanics. So here, E. How to obtain the E? Okay, because we know E is negative gradient of potential, right? So now I'm use potential. V, right? And then potential V is gradient of minus E over, sorry, this is potential energy. Okay. Minus potential energy. Here, the potential energy, this is potential, right? Potential energy is minus E So we have E is now negative, negative became plus E, 1 over E. Okay, and now this one is 1 over E. Gradient, I'm going to use radial or spherical coordinates, that is the derivative of potential with R, with radial, but directions be along the R. So this is R divided by R is R hat, right? Because this vector along this radial. This is R, right? This is R. So here, this gradient is, I'm going to do derivative with respect to R, absolute value, and multiply this direction, unit vector, right? Okay. So up to here. Now, so then finally we can write B is 1 over, here I have E, right? So 1 over E M E C, 1 over R. Okay, R here, and D way dr cross with this one. And here, those are numbers now, right? Because this number is the direction. So now here, that equal to, you see the R cross, that is angular momentum, right? So here, 1 over E M E C, and I keep this one, 1 over R D way dr angular momentum. Up to now, we can write down Hamiltonian and go to the spin orbital coupling. So I use HSO. It's due to the spin orbital coupling of electron with the proton. So that's be negative. This spin magnetic moment, inner product of spin magnetic moment with field, right? So now here minus magnetic dipole moment, if you remember, that's negative E over M E C spin. That's why I say magnetic dipole moment, the opposite direction is spin, and with this factor here, and inner product B, right? So minus magnetic and plus. Now we have a plus. Now B is here. So now we have here. We have E over M E C, and that one is E over M E C, 1 over R, D way, and R, and here is S with L. So that is inner product between spin and orbital. That is coupling, right? That is here. Now we call spin orbital coupling. That comes here. Okay, but remember here, this is at this state. At the rest of electron. Rest of electron, right? But in general, we want to transfer to the rest of realm of proton. So we are going to convert or transfer this one to that one. Then we are going to transfer to the rest realm of the proton. Yes. So how to do that? Now I'm going to, again, I still use, because the notation has the same, so even though they are same notation, but now we have different. Now I'm going to give you, the only difference is that when we transfer, since we know this transfer is the velocity that is in the relativistic very fast. So that transfer is taken account that relativistic condition correction. So just 1.5. So just half of here E cancel, right?
Is S here the pointing vector?
Which one?
S?
This is spin.
Oh, that's the spin.
Yeah, that's here from here spin. Square and 1 over R d v dr. So d v dr. S. No. So now this is a concept. This is a so-called this name Thomas's precision. Thomas. Let's see. Consider okay. We will not spend too much time here. What we need to is this component. Okay, now that is the correction. So in quantum mechanics, we just make this hat, right, as operator. The operator of this spin optical coupling is that term. Now it is S O is half of MEC squared and 1 over R EA R. Now this is spin optical angular momentum and optical angular the products. So this is what we have, this one. Now, not finished here, this one, right? So not because potential, this is the hydrogen, right? Potential operator is the interaction between the electron and the proton, right? Is this one. So E ray R is R squared E squared, right? So here finally we have the spin optical coupling is here we have R cubed and E squared equal. So we have 2 and E C squared E squared 1 over R cubed and inner product of spin optical and optical. Okay, that is we reached here, so the remaining part we are going to apply the perturbation. So now, if we only consider spin optical coupling, so now the total Hamiltonian of the heavy atom is H naught plus H spin optical coupling. Okay, H naught, we know that is the momentum, two terms, momentum plus potential, right? That is H naught, and then this one. Very familiar with this, right? Chapter 7, we deal with this coupling, so you know how to replace. Now I'm going through it, right? So here, this one H naught, right? I just like to remember, so now I still keep H naught here. You know that is equals plus. So that one, we have half of this one is this, that one is half, so that is we have factor 4, because 2, so now MEC squared E squared 1 over R cubed. And then this one is G squared minus L squared minus S squared, right? Now, let's look at the joint eigenstates. If they are commute each other, then we can immediately find the joint eigenstates. Very easily you can find that correction term. So now, H naught, here square, L square, and S square, evenly at G, Z. Are they mutually commute? Right? Since H naught, here H naught, remember if you want to, in the spherical coordinates, that is the radial part of kinetic energy PR plus angular momentum L squared, right? So that means PR commute with all elements because independent, and L squared commute with those, right? So H naught commute with this. Actually, I don't need this one. Not just H naught, so because they commute. H naught commute with this, and they are all commute, right? The remaining part, this part, is those, so they come in, we already start. So the joint eigenstate immediately can have the result. Joint eigenstates to be this index. Okay. That N index is for the real part, right? The H not the real part. And the remaining is angle part. Angle part we have a G. Okay. Okay, let's use the notation. So first L, S. Okay, like G1, G2, and G, right? And G, and GZ is, let me use A and G to distinguish. So we immediately know, we can analyze this the commutation between those each individual operators. We know they have joint eigenstates. So if they have joint eigenstates, very easily we can solve the eigenvalue problem, right? Okay, then this is we are going to find, right? So then the Hamiltonian apply this joint eigenstates. If it give us energy, right? We immediately solve because this is already eigenstates of the Hamiltonian. And now I'm going to give all the index. Since here you will see it depend on all index. That's not only depend on n. H naught is only depend on n, right? But now here, let's see in general. S, G, and G. This case is straightforward to make the correction. So now we are going to find this, right? But this is just inner product because it's orthogonal. S, G, and G is the inner product of the sandwich of this Hamiltonian between these joint eigenstates. Then we have each individual, we have H naught and H SO, right? Two terms. So let's look on two terms. N, L, S, G, N, G, plus N, L, S, G, N, G, H, S, O, N, L, S, G, N, G. The first one, we know H naught does not depend on L, S, G, and Mg. That is only depend on the quantum number n, right? That is higher degenerate. So that is E n naught, which we already know. And then now this part. So this part is here, right? This term. Now, this term, let's see how much complicated, right? So now first, okay, let me first add it on numeric type instead. SO, let me see. The correction to the first order is due to the spin orbital coupling. Now let's look at this term. We can write down this correction very easily, or straightforward, because it's a joint eigenstates of this. So how much it is? I think I copied. Okay. Yes, that I see. Okay. Since I know this one, the joint eigenstate in chapter 7. Yeah, chapter 7. So if you remember, that is psi n L plus minus half and mg, which is the radial part r and L, and the orbital element. Then we have a spin and the orbital. So these are two terms. There's also homework to play. 2L plus 1 and y L mg plus half, then the spin down, the spin part plus minus L plus minus mg plus half, 2L plus 1 here is y L M J minus half, then it's half. Okay, this equation is 7 to 13. After discussing after coupling with this space, if you remember this. Okay, the only difference here is mg. That is ml. So, but ml, mg, you follow this selection rule. So, okay, once we have that, now we are going to see this one. E and now, which is n, l, s, j, and g, h, now, n, l, s, j, and g, which is only between the n is minus e squared over 2 a naught n, or minus e naught n squared. That is first one. Now, second one, SO first. That is N, L, S, G, M, G, H, S, O, N, L, S, M, G, G, M, G. Okay, that's equal to here, this one, right? So we have a constant, let's take a constant outside 4 MEC squared. Okay. And here, N, L, and R2, N, L. Because that's the radial part here. N and L only, for radial part is this one. When I use this, it's radial function, right? And here, the R is only dependent on radial. That is this term, 1 over R2. And the remaining is angular part. So multiply the remaining is N. We don't need n, right? So now we only need this L, S, J, M, J. So here we have J squared minus L squared minus S squared, L, S, J, and J. So we need two parts, this one and this one. For this one, that's equal to 2 over n q L, L plus 1, 2 L plus 1, n r q, with this equation in chapter 6, that is 6 for 184. Then for this one, L, S, J, M, J, J squared minus L squared minus N squared. We know this existence of this, so we know. Now speed, J is J, we have H bar, right? We have H bar squared and J plus 1 is this one, right? And second one is L plus 1 minus S plus 1. That's all. Okay. And here, this one, since S is a half, right? So that is 3 and half, 3 and 4. Because this is a half, so that is 3 and half, and this is 1 half, so it's 3 and 4, right? So now let's combine together. Okay, another time. But yeah, I think this is let's see, we might have another class, so I don't want to stop it. I don't want to continue. Already 5 minutes almost. Okay, but almost. We almost finished. So then we have this O1. Then you will see how much contribution compared with this here. Compare this one, and you will see that is the perturbation term. Then next we are going to discuss the contribution from the relativistic. I looked at time is really hard for us for this chapter 9. After this, I really want to introduce variational principle, so that is very important, more practical. when we do the computational simulation in quantum mechanics. So at least I need to take one example, like helium atom or hydrogen molecule. Then we go to chapter 10. Hopefully in chapter 10, we need at least 1 week class, 2 class, or 2 or 3. So we have next week 2 class for the chapter 9, hopefully.
What is
But
the chapter 10?
chapter 10, I hope not till next week I can finish this chapter 9. And then perhaps week that is after next week, chapter 10, hopefully.
What is the topic?
The topic, okay. First topic, we are going to introduce a picture, like interactional picture, Heisenberg picture, and Schrödinger picture. That is important when we deal with time-dependent Hamiltonian. So with this picture, you will know how to do this. In particular, we are going to introduce interaction picture, and then this for time-dependent perturbation. And in this interaction picture, is more easier to do. So we first introduce this picture that may take half class or 1 class, and then we are going to discuss how to calculate the contribution from this time-dependent perturbation. That is, most case, like hydrogen atom, we have light come in, right? That then the electron excited to the high energy or jumped for high energy, so that absorption and ejection and emission. So that is a transition. Is related to this time-dependent perturbation, how to determine that. And that is important. Your experiment will need to know this transition, which associated with the selection rule. Yeah, hopefully. So chapter 11 definitely don't have time.
What was chapter 11?
Scattering.
Yeah.
So
So are those not the tornado sirens?
They are.
Yeah, they were there was a weather warning, right?
Yeah, he canceled E&M.
oh, cancel.
Yeah.
Oh, we can continue.
Why
You want to continue?
I'm more concerned that every tornado siren in the city is going off.
So you have to stay inside, right? Cannot go out, right?
I'll
Oh,
take my
sorry,
chances.
I have a meeting with Aswad at 5:30. I can only give you, I have to go back. Okay, sorry, I have another meeting. I thought I finished and I should talk to him. Okay, sorry. But go to the textbook, and next time I will skip.
That works.
Sorry, yeah, if I do not have a meeting, we can extend this kind. Yeah.
So there's actually a tornado.
Tornado warning issued for Jefferson County.
It's over or still not coming?
No, they've apparently cited a tornado over northeastern Jefferson County.
Right now?
Yep.
Oh,
They just sent out a rave alert.
okay.
Stay inside.
So how can you go back? You have a car?
Oh, yeah, I drive.
How about you? You have to walk?
We have.
Oh, okay.
Jacob's the chauffeur, he's the cameraman, he's the chauffeur.
Really?
He is nice.
Did you pay them? Pay them to pay.
Looks scary outside.
Yeah, now it's like very quiet, so you have to go now. And hopefully
Yeah.
before the new
Oh,
store,
so
some store comes, it will be already
so in
unbooked.
apartments also they
Thank you, Dr.
sent out
You will
siren.
come. I have to another meeting.
So up to 5:45, right? Yeah. So there should
I
be a tornado.
bring my umbrella.
Don't go outside.
We
Stay inside.
Okay,
Like COVID.
see you.
Have a good day.
Yeah.
We will go to the basement. So have you ever seen a tornado?
I've never seen one, but I like that we're like, is that the tornado siren? She's like, oh, do I have more time? that's a perfect Dr. Yu right there.